Continuing on with section 13.4, applications of linear systems, we're going to do a few problems in this section that have to do with motion. When motions work together, they are added, but when they work against each other, they're subtracted. So here we have an application problem that has to do with motion. Now this is a tricky one, but it reads about a jet plane traveling with wind. And if you know anything about traveling with wind in your face, it slows you down. Or on the other hand, if you are traveling with the wind at your back, it could speed you up. So it tells the story about a jet plane traveling with the wind. That means the wind at its back helping it along. And on the return trip, the plane flies into the wind, against the wind, and his travel time increases. Find the speed of the jet plane in still air and the speed of the wind. So what this is saying is, if there was no wind at all, which is another way for saying still air, if there was absolutely no wind in either direction, it wants you to decide the speed of the jet plane. And then it also wants the actual speed of the wind. So as we talked about the very beginning video, how to set these problems up, you have to determine what it is you're trying to find, which is the speed of the jet plane in still air and the speed of the wind. And then we assign variables. So we're going to assign a variable for the speed of the plane in still air. So I'm going to make it an R just simply because R will stand for rate. So with no wind, that would be the speed of the plane. And then I'm going to pick another variable W to represent the speed or the rate. I can use the word speed and rate interchangeably of the wind. So if I were to put the wind with the rate of the airplane, the motions are going to work together. The wind's going to help the plane. So the speed of the plane with the wind would be R plus W, and the speed of the plane against the wind would be R minus W. So what I now know, using the formula distance equals rate times time, the distance that the plane traveled was 1,950 miles. That's the distance, which equals the rate times the time. So with the wind, the rate is R plus W. So that's rate times time. And it says the time of going with the wind is 3.9 hours. So that's my formula for the going with the wind. I can also make one going against the wind. On the return trip, it doesn't say, but we know if you're going there and going back, you're going to travel the same distance. So the distance on the return trip would also be 1950. Now the rate is going to slow down against the wind. So you subtract the wind speed, and it took them 5 hours to return. So I have two equations, and I can solve these for one of the two variables. So again, you can use substitution or elimination. It makes no difference. If you want to do either one, you're going to have to distribute these values. So I'm going to start with this one. 1950 equals 5R minus 5W. And then I also have to distribute this second one. 1950 equals 3.9R plus 3.9W. So these are the equations that I'm going to work with. I think elimination will be hard because these are decimals. So I think what I will do is substitution. So if I solve this for R, I can then substitute that into this other equation. So I would have 5R equals 1950 plus 5W. So basically I added 5W to both sides to get the 5R by itself. Then I'll divide everything by 5 to get R equals 1950 divided by 5 is 390. 5 divided by 5 is 1. So now I have something that I can easily substitute. R equals 390 plus W. I can substitute that into the second equation. Any place there's an R, which is right here, I will replace it with this value. So I have 1950 equals 3.9, and I'm going to put, instead of R in there like it is here, I'm going to replace it. I'm going to replace my dollar bill with 4 quarters. And then I still have my other 3.9W here. So now I have an equation with all W's. I'll be able to solve this for W. So I have 1950. I need to distribute this. 3.9 times 390 is 1521 plus 3.9W plus 3.9W. Combine like terms, giving me 7.8W. And I'm going to subtract 1521 from both sides. So when I subtract 1521 from 1950, I get 429. Now I'll divide both sides by 7.8 to get W. 429 divided by 7.8 is 55. So I found that W equals 55. Now we go back and remember what we set W equal to, which was the speed of the wind. So that's the one thing we found. We were asked to find the speed of the plane in still air and the speed of the wind. So we did speed of wind. Now to get the speed of the jet plane in still air, that's R. So I can plug 55 into one of these equations and solve for R. So I'm running out of room here, but I'll try and squeeze it in. I'm going to plug it into this one so I don't have to worry about the decimals. So I have 1950 equals 5R minus 5W, which is 55. So 1950 equals 5R minus 275. And I'm going to have to stop there because I've run out of room, but you add 275 to both sides, divide by 5 to solve for R, and you should get R equals 445. This next example is about delivering packages at two different price points. So what we have is a story about a shipping company. They delivered 160 packages total in one day. The cost of regular delivery is $6.50. The cost of express delivery is $17.50. Total shipping revenue for the day was $1,513. So this is a problem where we are going to have one equation that has to do with money and one equation that have to do with quantity. It asks how many of each kind of delivery were made. So that's what we're trying to find. So we're going to set our variables equal to what we're trying to find. So there is regular delivery. So I'll let X equal the quantity of regular deliveries, and I will let Y equal the quantity of express deliveries. In a day, they delivered a total of 160 packages. That's a quantity. So I could add the quantities together and get 160 because they told us that's how many they delivered in a day. So then my next question will have to do with price. So however many regular packages were delivered, it cost $6.50 to deliver each one. So I could say it would be $6.50 for every regular delivery, and it costs me $17.50 for every express delivery. I don't know how many there were, but I let my Y represent that quantity. The total shipping revenue for the day was $1,513. So my total price was this. So again, I have one equation dealing with money, one equation dealing with quantity. I have two linear equations now. These are both set in standard form. So I can try to solve this using substitution or using elimination. It's your choice. I would probably say, well, if I could multiply this x by negative 650 to get these to match. So I will probably just do that. So if I multiply every item in that top by negative 650, then I get these quantities, these coefficients in front of the x to be opposite numbers, so they're going to eliminate out when I add them together. Before I do that, I'm going to multiply 160 times 6.5, which gives me, instead of that, I'm going to replace that with the actual number, which is negative 1040. So when I add these, they become 0x, which is 0. When I add these, 1750 minus 650, I'm left with 11y, equals, and when I add these two, 1513 and a negative 1040, I get 473. Divide both sides by 11, giving me y equals 43, which tells me there were 43 express packages sent that day. I plug this in to one of the equations. I'll plug it in here because this is the easier one. You could plug it in here, but replace the y here with 43. So I get x plus 43 equals 160. Subtract 43 from both sides, giving x equals 117. So 43 packages, 117 packages. Check for reasonableness. It makes sense if we sent 160 total. You could deliver this quantity of packages. The next example is a solution percentage problem, and it'll be similar in the sense of the money, where we had one money equation and one quantity equation. In this case, we're going to have one percentage equation and one quantity equation. So this is where we're going to mix a strong solution and a weak solution together to get the optimal perfect solution. So it's saying that a chemist needs 8 liters. Now this is kind of a significant, they spell out the word 8, but that's going to be a quantity that will be important. 8 liters of a 50% alcohol solution. So that's what he wants to end up with. He wants a beaker that's 8 liters, and the concentration of that has to be 50%. But he only has a 30% one, a weak one, and an 80% strong one. So he's going to mix them together, the 30% and the 80%, to come up with a mid-range concentration. But we have to decide how much to mix together. Do we mix 2 liters with 6 liters? Do we mix 1 liter with 7 liters? Do we mix 4 liters and 4 liters? So that's the question. How many liters of each solution should be mixed to get this ideal solution? So what do we know? We know that when you mix the quantity of the weak and the strong, we need to end up with 8. So that gives us a quantity equation, but we need to set up our variables first. We're looking for the liters of each solution, so we'll let x equal the quantity of strong solution, which I'll say the 80%, and I'll let y equal the quantity of the weak solution, or the 30% solution. I know when I add those together, I'm wanting 8 liters. So I have x plus y equals 8. Now I'm going to come up with a percent equation. However much strong I need, it will be 80%. So the amount of alcohol in the final solution I'm looking for is 50%. So I have 8 liters at a 50% solution. When I add the strong solution, however many liters that is, it'll be 80% of that. And if I add that to however many of the 30% solution, when I add this quantity of 80% plus this quantity of 30%, I get 8 liters of the 50% solution. So here are my two linear equations. I can't use these as percent numbers, So I can convert those to decimals. So x times 0.8, or better stated 0.8x plus 0.3y equals 0.5 times 8. 0.5 times 8 is 4. So I have x plus y equals 8, and then I have this second equation, 0.8x plus 0.3y equals 4. So I can multiply all these by 0.8 so that I can eliminate. I could solve for y and substitute. But if I substitute, I'm going to keep these decimals, which I don't really want to have to worry about. So either way, if I multiply the top equation by, and I'm going to multiply by negative 0.8 so that they have opposite signs. So negative 0.8 times x plus y. So here I took my original equation, x plus y, multiplied the left by 0.8, and I multiplied the right by negative 0.8, giving me negative 0.8x plus negative 0.8y equals negative 6.4. Now I'm going to line my other equation up in standard form. 0.8x plus 0.3y equals 4. Add those together. The goal was for these to become eliminated. Negative 0.8 plus 0.3 is negative 0.5. Y equals negative 2.4. If I divide both sides by negative 0.5, I get y equals negative divided by negative will be a positive 4.8, which means I will need 4.8 liters of the weak solution, since I let y represent the weak solution. And then I can plug that into this equation to get the quantity of the strong solution, which would be 3.2, because I do x plus 4.8 equals 8, subtract 4.8 from both sides, and you get x equals 3.2. These are reasonable numbers. 4.8 and 3.2 together make 8 liters of the 50% solution. One last example. This is my kind of example. We're talking about burgers and fries. So Logan and Peyton went to Culver's for lunch. Logan ate 2 butter burgers with cheese and a small order of fries for a total of 1,801 calories. When you hear the total quantity, that should make your brain probably think you're going to add 2 variables together to get that total. Peyton ate something different. How many calories are in the butter burger with cheese? And then it also asks how many calories in the fries. So identify what you're looking for, which are calories in the burger, calories in the fries. And we're going to let variables represent those. So we are going to let x equal or represent the calories in the butter burger. And we'll let y represent the calories in the fries. So if Logan ate 2 butter burgers with cheese and 1 order of fries, you could represent it that way. However many calories in the Butterburger. He ate 2 of those, 1 order of fries, for a total of 1,801 calories. So I have a calories equation. Then Peyton ate 1 Butterburger, so 1x, and 2 fries for a total of 1,313 calories. So in this case, they're both calorie linear equations. Some of the previous ones we had, one was a quantity and one was a percent, and the previous one before that we had one was a dollar value and one was a quantity. This one has both quantities of calories. So I have 2 linear equations that can easily be solved. I've been doing elimination recently, so I'll choose to do substitution in this one just for variety. So I'm going to solve the first equation for y. So I'm going to subtract 2x from both sides. So I took this and I solved for y, subtracted 2x from here and 2x for here to get the y by itself. So that's what I did right here. Now this is what I'm going to use to substitute. Anytime I see a y, I can replace it with this, which means I can put that right into that. So I can say 1x plus 2 times, now I'll do the substitution value, 1801 minus 2x equals 1313. So I have all x's now. I can distribute this. X plus 1801 doubled is 3602 minus 4x equals 1313. Combine these two like terms and I get negative 3x plus 3602 equals 1313. Subtract 3602 from both sides. Which gives me negative 2289 on the right side. Divide both sides by negative 3, giving x equals 763. So it probably sounds reasonable that 763 calories would be in the burger, especially if you ate 2 burgers and fries and had 1,800 calories. So that sounds pretty reasonable. I can plug this back into either one of my equations to get the y value or the calories in the fries. So 2 times 763 plus y equals 1801. 2 times 763 is 1526. Subtract 1526 from both sides. And I get 275. So I get y equals 275, which represents the number of calories in fries, which sounds reasonable. If the burger was 700 calories, the fries were 275. If I plug these into both of those and check them, I will know if I had the correct numbers.